Alright, so I am going to finish up what we didn't finish in class, which was, I believe, this guy right here. So this is the last piece. Starting off, we talked about that I wanted to show you that a probability tree is really nice because you can multiply across branches. So if I want to find the probability of the first one being green and the second one being red, then I can do 6/10 multiplied by 4/9, and so on. The probability of, let's do that in a different color, the probability of red and green would be 4/10 multiplied by 6/9, and then the last one, the probability of red and red, would be 4/10 times 3/9. So each of these, what's nice about a probability tree is if you do it correctly, let's see, so that'd be 30 over 90, 24 over 90, 24 over 90, and then, what is this, 12 over 90. You should have incorporated every single possibility in the sample space in a probability tree. Therefore, if done correctly, your total should be 90 over 90, a probability of 1. The probability of everything in the sample space is a probability of 1. Okay? Hopefully that worked out. 40, 70, 80, 90. Okay. Conditional probability, another example. So this is one, you'll see something similar like this on most probably your external. What they usually want to do is deal with probabilities given. They may give you a situation, and so conditional probabilities can be word problems. They can do conditional probabilities straight through notation. So let's take a look at this guy. Airline, the probability that we depart on time is 0.83, arriving on time, that it both arrives and departs on time is 0.78. All right, find the probability that a flight arrives on time given that it departed on time. So, probability that it arrived on time given that it departed on time. So, that's going to be the probability of the intersection divided by the probability of departing. And the reason that that is, actually, I'll talk about that in class tomorrow. So, the and probability we have, and that is 0.78. The probability of departing is 0.83. All right, letter B. The probability that we depart on time given that we arrived on time. So that would be probability of departing and arriving on time divided by the probability of arriving on time. So this one would be probability of departing and arriving. In this case, order doesn't matter because whether you arrive or depart, that's pretty much what they're asking you on time, and then divided by the probability of arriving on time. Okay? Next, independence. So there are, I believe, two different ways that we can talk about independence. So there was the basic way that we already discussed, which is if two events are independent, then their intersection, their intersection will be a strict product of the separate probabilities. Okay? The other definition of independence is the fact that the probability of A given D is equal to the probability of A itself. So what this says is it actually doesn't matter that some other event occurred first, event D in this case. It does not matter that it happened. The probability of A occurring still happens regardless. And this, there is a little mini proof that goes along with it. If events are independent, then the probability of A intersection B is the probability of A times the probability of B. So I'm going to add into the front of this that the probability of A occurring with B already occurring would be the union divided by the probability of B, which cancels. So that's the mini proof. So are the events arriving on time and departing on time independent events? So all you have to check is one or the other, but probability of A, given that D occurred, was 0.78 divided by 0.83, and the probability of A is equal to 0.92. So that is definitely not the same, but I will show it to you just in case you don't believe me. 0.7, wow. Maybe I won't be showing it to you. This guy is frozen. Let's try it one more time. 0.78. Okay, just kidding. So these are not equal values, therefore not independent. Or you could have done it the other way, probability of D given A, because that was this part B. You could have used that to prove it also. They both do the same thing. I believe that is the end of it. Oh, no, this was my example that we could go through. It is also in your textbook, but let's talk about, in many countries, the police stop drivers on suspicion of drunk driving. The stopped drivers are giving a breath test, a blood test, or both. In a country where the problem is vigorously dealt with, the police records show the following. 81% of the drivers stopped are given a breath test. All right. So, let's see. Timing-wise. All right. So, I am very sorry, children. I actually have to run to a meeting, so if I can come back and finish this, I will. If not, it is uploaded, and this is in your textbook, and I'm going to ask that you read the example, walk through the example before you try your homework, okay? If you have any questions, I can definitely go over it in class, but hopefully if I have time to run back after my meeting, I will record the rest of this video.